So we're pleased to have Simion and Filip, who's going to tell us about the Kontsevich Zorich Cocycle.
So first of all, thanks a lot to the organizers for bringing us to this very beautiful place and for letting us speak on these things that many of us like. So as I said, as the title says, I'll be talking about the Kontsevich Zorich Cocycle, but I will begin with just some motivation, and in fact it will be very connected to what Samuel was talking about. I was a little bit even worried that he's going to do half of the first half of my talk. Luckily he sort of took a different route. I also have to warn you that the word infinite will only be heard in this sentence because I'll not be saying anything about infinite area surfaces, but I do hope to explain why the result mentioned at the end by Cocycle and Eskin is true. So why is it that we can replace for almost every AB by actually something happening for every AB? But I'll talk more about this when I get there. Before this, so let's start again with the square, which we'll think of as the torus. And we'll consider again the flow in the direction theta, which wins out in a fashion like this. And we're going to ask the following question. What happens when you take a very long trajectory on this torus and you close it up? So we'll think of this thing as happening on the C2 lattice in R2. So here's our flow, and it's going on for a very long time. And imagine this picture also going on this torus. This thing is winding around in a very complicated way. And you stop it after some very long time t, and the end of the trajectory lives somewhere here. You pick one of these endpoints, say this guy, or say this guy. You close out the trajectory, and now you have a closed curve. So I'm going to denote this tip of the curve by gamma t. And now you have a closed curve on this torus. And you could ask, what is its homology class? Like, how, that's one way to measure it. It's a curve of length t, but you can ask what's the length of this curve. So, what's the representative of this class in homology? And you expect this thing to be of order t because you've been running for time t. And I should note that I could have chosen pretty much any of these guys, and up to some bounded error, I would get roughly the same class. And the question that's more meaningful is to consider this limit. So what is this thing? And if we introduce, if we call this lattice vector, so this is 0, this is A, and this is B, then you won't be surprised to find out that gamma t has coordinates t cosine theta and t sine theta. This is where this tip is lying. And the coordinates of one of these guys are going to be roughly the same up to plus or minus some very small error, like of order 1. And when you divide by t, you can see that the 1 over t times this class will cancel. And so this thing will be roughly cosine theta, sine theta. I should just put an approximate sign. In the limit, these things are actually equal. Where I write two coordinates for the coordinates A and B. Think of these things as homology classes. All right, so this question wasn't very difficult, but how about we ask the following, which is a little bit more interesting. So as you've seen, it makes sense to always consider, to just normalize things and always consider vertical trajectories. So this is going to be our gamma t. But instead consider a different torus. So now I'm not going to consider a square torus, but rather some skewed lattice. So my drawings are not as good as for a torus, but you can sort of get a rough idea of what this thing looks like. So you have this lattice. And now there is no particularly nice choice of A and B, the basis vectors. But say you call this guy A, say you call this guy B, and you ask in the basis AB, how does the homology class of gamma T look like? How does it look asymptotically? And so this is now a much more meaningful question. So here, this is not just a rotated square. It's actually a rotated thing that looks like this. So it's a parallelogram that you rotate and you have this periodic structure. So to answer this question, it actually makes sense to look at the space of all such lattices. And it's a very remarkable fact that, if you haven't seen it before, is that answering the question of the individual behavior of this single trajectory on this fixed torus can be related to the behavior of a very different dynamical system. So you look at the space of all tori, which you think of as H, the upper half plane. So you can think of the lattice being generated by, if you have your parameter tau here, this is the lattice. But notice that we allow the thing to be rotated. So really we're looking at the unit tangent bundle of H. So this is the space of all tori, of all marked tori. This is what H represents. But if we look at the fundamental domain, so if we could forget about the marking and we just remember the lattice, then we have to quotient by the action of SL to Z. And we get this fundamental domain. So we have this picture of this tooth that lies in the upper half plane. And this, for example, this lattice corresponds to some value of the parameter tau somewhere in here. And the fact that it's rotated in some way, in fact, corresponds to some unit tangent vector like that. And what we're interested in is trying to, so remember, the question was how does this geodesic behave? So one thing which at first might seem strange is to apply the following transformation. So we'll take the transformation G lambda, which is going to be e to the lambda, this diagonal matrix. And we're going to apply this matrix to this picture. And so what is this matrix doing? It's shrinking the vertical axis, the y-axis. This thing is getting multiplied by e to the minus lambda. And the x-axis is getting expanded like this. So this is what's happening in this picture. What's happening here is that, so this guy, another picture for this is that you really have the modular surface, which looks like this. So it's a complex surface, but it has these two special points corresponding to these guys. So there's the square here and the triangle, if you like. And so we're really looking now at what happens if you apply the matrix G lambda to this picture. In this picture, what's happening is you're really doing the geodesic flow on this surface. So you have a unit tangent vector, and you're flowing in some way. Maybe you come back, then go there, and then after applying this G lambda, you end up somewhere like here. And what does this correspond to in that picture? Well, I'm trying to redraw the picture. So our gamma of t now, let's say that we took lambda. So I'm going to take lambda to be of order log t. So when you take e to the log t, basically you've brought this vector now became length 1. And so this thing, so this is g lambda, the tip. But so this seems nice, but the problem is that the basis vector has changed, and it has changed very dramatically because you've taken this vector and you've multiplied the x coordinate by some, by e to the lambda, and the y coordinate by e to the negative lambda, and so these guys now look something like this. They're very distorted. So you have g lambda of A, g lambda of B. But the lattice itself, so notice, however, that the lattice itself does not need to be very deformed. So if you apply this matrix, the lattice itself could be a perfectly nice lattice, even though this matrix, this lambda could be rather large. So you still have some lattice. which need not look at all like this lattice, but it doesn't need to be at all deformed in any way. So you can pick another basis. So let's call this A prime and B prime. And now what you have is a transition matrix. So you have this basis G lambda of A and G lambda of B. And so this is your basis. And you apply a transition matrix M lambda, which brings you to this basis A prime, B prime. And the point is that now this vector G lambda of gamma t is, in this basis A prime, B prime, it's a relatively small vector. It's, say, a vector of length 1. And so the point is that if we knew what this matrix M lambda is, how this matrix looks like, it's an integer matrix, or maybe I should say, M lambda belongs to SL2Z. If we knew what this matrix looked like, then basically we would know that this vector that we're interested in, gamma of t, is obtained by applying this matrix M lambda, or rather its inverse, to a vector of not very big length in this basis A prime, B prime. And so we could, for example, diagonalize this matrix M lambda, and if it had some specific eigenvalue, then basically this vector gamma t will be oriented along that eigenvalue. So then we could estimate how this guy looks like in this basis A. So the points that I want to take away from this, so the sort of structural things that will be useful for what I'd like to talk about are the following. So we have this picture of the modular curve, and we think of each of these guys as a torus, and we forgot the marking, but locally, if we fix a marking, locally near this guy, we always have an identification of all the markings. So if you think of a basis sitting on top of this point, as you move around the loop in this torus and you get back to where you started, if you locally, so it's this picture that you've seen in complex analysis probably, when you do analytic continuation, locally you can identify things. And if you keep doing it, when you came back to where you started, the identification is between the new basis and the old basis is by some matrix M lambda. So what the structure that you have is that you have this X, which is, so the tangent space, as you saw in the previous talk, is just SL to R on SL to Z. And over this object, we have this bundle of, so it's the first homology of the torus. So it's a bundle of Z2, it's a bundle of just Z2, the group Z2, but as you go around loops, things get glued in some mysterious way. Well, it's not so mysterious, they're actually glued, so to each loop there corresponds an element in SL2Z, and they're glued exactly by the matrix in SL2Z that we have. So this is one piece of the structure, and so this bundle, so this is pretty much, this is a topological piece of the data, but there's an extra piece which is very important for what I'll be talking about, which is that if you look at this lattice, you can think of this as an elliptic curve. So this guy, if you think of this as just a Riemann surface on dimension 1, you have the natural holomorphic one-form DC which lives here. And so, let me just write the data here. So we have X, and over this you have the bundle of, so now I'm cheating, I said homology, but I'm going to look at cohomology. And you have it with, say, Z coefficients, but you can also consider the same bundle, but with complex coefficients. So I'm just going to denote it like this. It has the same structure, you still have the same local identifications. But now inside you have this space, which I'm going to denote by H10. And H10 is the span. So DZ gives you a span, a cohomology class, which you can, so if you integrate DZ, if you integrate it along the A direction, you get the number 1, but if you integrate it here, you get the complex number tau. And so this tau, as you see, it's moving in the upper half plane. So these things, this bundle H10 is not you don't have these local identifications. It's actually moving in a very nonlinear way, and in a very interesting way in some sense. And so what my talk is going to be concerned about is how this thing behaves, and how can understanding this bundle can actually tell us something topological about this guy. So this is the setup in this specific situation. So the point is that understanding the geodesic flow on this modular surface and how it acts, how this matrix M lambda behaves, will allow us to answer very basic questions like the things that people ask, for example, in the Winching model. How does this trajectory geometry behave? So the general setup is as follows. So you have flat surfaces which are just glued polygons. So you take something like an octagon. Sorry. By the end it'll be an octagon, but yes, this is, yes. You take two pentagons and say you identify them like this. Oh no, this is terrible.
They should be narrow.
Yeah, they need to be parallel, as someone is correctly pointing out. So, yeah, so now this thing is identified with this guy is identified. So these two guys don't look parallel, but they should be. So should these two guys, and this should be parallel to this, and they should be glued together. So you get some surface like this, and the general situation is, so the totality of such things is usually called the strata, and so it's this letter H with index kappa. So kappa is a multi-index, so you have K1 up to Kn. These are singularities. So everywhere here you have this flat metric, and you have this form dz that I was talking about earlier, but these singularities are these home points where locally this form, if you write it out, this thing will look like, it will have a zero. It will be a homomorphic form, but it will have a zero of order K1 through Kn. All right, so this is the general structure. So you have these polygons, and they form some total space, which is denoted by HK, and you have an action of SL to R on this HK, H comma. And the action is just, so geometrically you just act by a matrix and SL to R, you act on these polygons. They get skewed in some funny way, but lines which are parallel will stay parallel. They'll have the same length, and so you can glue them together and get a new surface. And understanding this dynamics is somehow central to understanding, and understanding the dynamics of this action on this big space is important for understanding dynamics of just the vertical flow on a specific individual surface. But the important thing is that you also have the same structure as before, so you have what people call the Hodge bundle. So I'm going to denote, so this is the same object but with different coefficients. So this is, the lattice is just above, so when you glue these guys together, you get, so you get a surface, so I'm denoted by S and lambda. This is in the stratum, and so S is a Riemann surface. And lambda is going to be a homomorphic one form. And so you have defined in this way, as we had it in the upper half plane, you have the homology of this Riemann surface. So H of T is just the homology of that, sorry, the cohomology of S. And inside H of C, you have again the space H10, which is the space of holomorphic one form. So this is a Riemann Riemann surface. So inside the complex cohomology, you have the representatives given by holomorphic one form. So this is a subspace, which again is moving in a very interesting way. So it forms what people call relational point structures. And so what this literally means is that you have a bundle which has this local identification between the fibers, and inside of it you have this moving subspace which is moving in some interesting way. And again, what's quite surprising is that understanding this bundle, understanding just this flat connection, so I should have said, I still haven't told you what the Kontsevich Zorich cocycle is, but it's this thing. It's either of these three guys. It's usually called the Kontsevich Zorich cocycle. So it's just the procedure by which you move one basis near the other surfaces. So it's in some sense surprising if you think about it that you have this purely topological object, and inside of it you have this complex analytic bag, and somehow the behavior of this topological object is dictated in many ways by this complex analytic part. So to understand dynamics of this action, so one of the main goals is understand invariant measures. Because if you understand invariant measures, then you can say things about the ergodic theory on these individual flat surfaces. Now, to do this, you have to
measures on what?
Measures on the strata concentration. So this is some topological space. In fact, it has a lot of nice structure, and you have this action of SL2R on this stratum, and you want to understand what are possible measures which are invariant under this action. So understanding these guys will tell you in the end things about individual flat surfaces. And so recently there has been a fair amount of progress in understanding this. And so there's the following general theorem of Eskin Mirzakhani, but to describe it I first have to tell you about local coordinates. So on this space, on the stratum, as I said, you can think of these things as locally as given by the data of polygons and how they're grouped. And so if you want to introduce coordinates, you can just think of the length of the sides. So if you record all the lengths of the sides, and the gluing is something that locally stays fixed. It's not, if you make a perturbation, you're not really changing the, you can still do the gluing as long as the sides, as you prescribe the sides correctly. And so the lengths of the sides, you can think of them as vectors in R2. And so obviously they have to have some restrictions. So the length of this side, so if you make the sum along this face, the vectors should sum up to 0. And also this vector is constrained to be the same as this vector. So you could do this, you call this in a complicated combinatorial way, but the nice way to say this in some invariant way, which doesn't depend on the choice of this decomposition, is that near the surface S lambda, you can give coordinates by the first cohomology group of this surface S, and so you have to take relative cohomology. And by R2, I just mean vectors in R2, and where sigma is 0 is the locus of zeros of lambda, or the same thing as the cone points. So you could think of having this surface, and so you have these marked points, and if you can prescribe the lengths of all of these vectors, and so also as you go around the loop, prescribing these things will tell you how the surface looks like. You will be able to unfold it and cut it into polygons and obtain a surface. So locally these give you coordinates, but of course you can see that if you start shrinking, for example, this vector, once it hits 0, there's a degeneracy. But hitting 0 is not the worst that can happen. I mean, you can imagine that this complicated gluing can degenerate very quickly if you move around these vectors. But locally, in the tiny neighborhood, you have these coordinates. So the theorem of Eskin Mirzakhani is the following. So suppose that mu is an SL2R invariant measure, so ergodic, I should say, on this stratum H kappa, then what their theorem says is that there exists, so locally, so if you look at this measure locally, there exists this subspace. It's a real subspace inside the real cohomology of this surface. So in these coordinates, so notice that you only have, I'm only taking one R here and not two. So there exists this subspace such that mu is affine, it's basically an affine measure on Ex, and then so you have this vector space, which is just this guy, but you tensor it with R2, so you take now R2 coefficients. And so this measure is basically given by a real subspace and by some affine measure on that real subspace. So that's informally what their theorem says. And in fact, they've proven some stronger results, but I don't really want to talk too much about them because they're not directly related to what I'll be talking about. So one thing which has been really important, and also this work, but also in understanding these things called Lyapunov exponents. So I also hope to explain this 2/3 that was raised at the end of the last talk. So this 2/3 is basically a Lyapunov exponent of this Kontsevich Zorich cocycle. So it gives you a rate of growth of some of these vectors. So I'll get back to that in a moment, but the point is this. So we have this Kontsevich Zorich cocycle. Which, as I said, was HC or HR or HC. So this is a flat bundle over the stratum H comma. And so by flat I mean that if you take a point, you can take any other nearby point, and there's a very canonical way to identify the fibers of this vector bundle, or in this case, if it's C, it's Z1. And so you can ask about what are other bundles, what are the subbundles invariant, which are invariant. So what do I mean by this question? Well, I'm saying that, so you have this vector bundle which lives over this space HK, and you can ask what are the possible subbundles inside of it, so that when you move them using this flat connection, when you move them along the SL2R orbits, they're constant, they're not changing, they're the same bundle. So by a subbundle, I mean just a assignment of subspaces above each point, and you get the same subspace if you move things around. Is this, do you understand what I mean by this invariant subbundle? So maybe I'll try to make this a little bit.
But they don't have, subbundles have to be flat or not?
Yeah, so if they're flat, they're necessarily invariant. But if they're invariant, they need not be flat. For example, there's the tautological, like the thing that gives you the SL2R action. That's invariant, but that's not flat. And so the interest in these bundles is really related actually to trying to do this kind of measure classification, or when you try to actually understand the fine ergodic properties of these objects. So maybe I should give a quick example, which is that of Deligne curves. So these are SL2R orbits. So, well, maybe I should just say they're the closed SL2R orbits. So you have this action of SL2R in this space, and in principle, it's like the irrational rotation on a circle. It has, you can imagine things, in general being very chaotic. But occasionally, you have these closed orbits. There are these special surfaces, which, under the action of SL2R, they basically come back to themselves. So you get these kinds of objects like SL2R mod some discrete finite covolume subgroup which sits inside the stratum. And so a lot of people have worked on this, and many of the results of the form that I'll be talking about have been due to Moller in this case. And they're related to the fact that these diagonal curves, they're not just these closed orbits, they correspond to Riemann surfaces. And Riemann surfaces are necessarily algebraic. And so, you can write them down with polynomial equations. And so then you can appeal to a lot of theorems in algebraic geometry to study these things. And so using that, Moller and other people have shown that these things have interesting arithmetic properties. And so what I'll be talking about is some analogs of these results. In fact, most of those results, more or less, transport to the case of these invariant manifolds. So when you have this measure, as I said, it's supported on this subspace, and basically it's supported on a manifold, and the support of this measure is called an affine invariant manifold. So, all right. So basically the theorems, let me just say the theorems, and I'll explain what they sort of mean and how you can apply them. So the first one is the following simplicity. So it says that this bundle H1 decomposes as a direct sum of, so the only way you can have invariant subbundles is as follows. So you have Pi is a subvector bundle. So it's SL bar invariant. Wi are the vector space. And so all of these guys carry punch structures, which just means that they have these homomorphic subbundles inside of them. And the fact is that any other invariant, so SL bar invariant subbundle has to be of the form. So the only way you can form invariant subbundles is by picking subspaces, subvector spaces inside these Wi's, and then you tensor them with VI's. And this is the only way that such a thing can occur. So this seems a little bit mysterious if you haven't seen it before, but this is basically, if you've seen representations of finite groups, it's saying that any representation of a finite group splits as a direct sum of irreducible representations. And these VI's, these vector spaces, are supposed to account for the possibility that there are several copies of the same representation inside. And so this is kind of what the theorem is saying. I want to make two remarks which are important for applications, which are that the same facts are true. So the same theorem is true, but so they're true for any tensor power of this vector bundle H1, this Kontsevich Zorich cocycle. And so this was for, so I should say that this was for SL2R invariant bundles. And it's also happening in the measurable category. So these subbundles in particular, they're allowed to depend measurably on the base point. So, and measurable is what you're facing when you're doing your quadratic theory. If you try to produce invariant subbundles, usually your quadratic theory will give you something that is measurable. And so this decomposition is also a priori measurable. But the same theorem holds also for tensor powers of this H1. And the reason why this is useful is the following. So there's a corollary of this thing, which is that if you have, say, P inside H1, it's some SL2R invariant subbundle, then in fact it is measurable subbundle, then in fact it is real analytic. And you might think that this is not saying too much, but one analogy which you can try to think of is if you know the proof of monster rigidity. When you prove, for example, monster rigidity, you get a measurable map between say the Riemann sphere itself, and you need to prove that this measurable map is not just measurable; it in fact turns out to be real analytic. So this kind of result that something that is a priori just measurable has to be a real analytic is really like it's a very strong rigidity property of these bundles, which has implications for the dynamics. So now I can explain why is it that this particular corollary. So corollary plus the Eskin Mirzakhani measure classification. So these things allow, these allow John Chaika and Alex Eskin to prove that to show the following. So I'm just going to say it first for people who know what this means, that the Oseledets theorem holds for all flat surfaces in almost every direction. So this all replaces what before was almost every, and this is the analog in Samion's talk of when he said that some theorem was true for almost every AP. These kinds of results allow you to show that it holds for all AP. And so what is this Oseledets theorem? Well, it's actually, to explain it, we just have to go back to the question we started off in the beginning. So remember, we're asking about the asymptotics of this cycle. So we had this flat surface, in that case was a torus, and we looked at this straight line as it was going around the torus, and we asked, what's the cohomology cost when you close it up? Well, if you take a different flat surface, so this is where I'm not very good at drawing. So let's say you take something like this, and you again launch this guy, and so that's not very good. Comes back here. So you can ask, how does this guy wind around the surface? So now this is, when you do the gluings, this becomes a surface of genus 2. And if you ask this curve gamma t, so the class and cohomology of this gamma t looks like this. This is what it means for the Oseledets theorem to hold. It says that this gamma t looks like t times some class, let me just call it C1, plus to the lambda 2 times some class C2 plus and so on. So if you're on the surface of genus G, you'll have G terms, G homology classes. And maybe I'll just,
Oh,
yeah.
don't erase that because I had questions.
Yeah, okay. So, so these lambda i's, so the first one is just lambda 1 and d is equal to 1. And these things are called Lyapunov exponents. And you'll probably see more of them in the wintry lectures. But, so by the way, this inequality, the strict inequality is due to Forney, and before it was, in some specific cases, it was due to Feach. So these are the numbers which govern the asymptotic behavior of this cycle. And the fact that you saw 2/3 means that some Lyapunov exponent is 2/3. So the first one is, say 1, but then something like, well, maybe not the Lyapunov exponent, but some expression in these numbers will lead you to 2/3. And the possibility to even compute these numbers is in fact related to understanding these kinds of invariant subbundles. So the only way to compute these kinds of numbers is related to the complex geometry and to the variations of Hutch structures that happen here. Okay? So, so this is one class of results that I wanted to talk about. Yeah. So, there's another theorem which I want to state, which is a corollary of this kind of stuff. So again, this is most, so I won't say much. If you've seen Muller's papers, you know where this is coming from, but the fact is the following, that affine invariant manifolds so when you look at them, they parameterize Riemann surfaces whose Jacobians have real multiplication. So there are a lot of words here which unfortunately I can't explain, so it doesn't have real multiplication. And I need to tell you what the field is, and it's what's called the field of affine definition of this affine manifold. So, so what this theorem is saying is that these Riemann surfaces, which correspond to these invariant manifolds, have to have some extremely special and very rare in general arithmetic properties. What this specifically means is a little bit more delicate. So, so I think some people in the audience know what this means, others don't. If you don't worry, it's not something crucial for for dynamics. It's not something very special. So, all right. So we have this these semisimplicity results. I should also mention that the semisimplicity, the result that I had here, and which I erased, and I shouldn't have, is that so some people some version of this result would have followed if we knew that these affine invariant manifolds are algebraic, that they're given by polynomial equations when you consider them in certain situations. But and by polynomial equations, I don't mean given by linear equations, but in some very strong algebraic sense. And this is currently not known, but in fact, this theorem, which I erased, but this theorem is stronger than what you would get if you had the algebraic fact. And also, the algebraic fact, I think that you get is, it can be deduced from this theorem.
Sorry, so you say the algebra, so you know that all the affine invariant manifolds are algebraic?
No, so I was saying that I don't know this,
Yeah.
but even if we knew, the facts that would be implied by that would be weaker than
the dynamical facts that you're interested in.
Yeah, so the theorem that was here, keep pointing at the board, is that so it says more than what you would get.
It says more in a certain direction. It doesn't say they're algebraic.
So you could. It says more than Deligne semisimplicity. That's what I'm saying. So.
Can I ask about the theorem that you?
Yeah.
So you have a. So we start with H1. We decompose it as a sum of tensor products, where the first part is invariant, and so we have these sort of VIs that we can identify.
Yeah. Maybe just yeah.
And then so then you say that any other invariant subspace can be, and these come from having Hodge filtration.
Yeah.
So and then any other invariant subspace is made up of VIs plus a tensor WIs, but that is at the measurable level at that point.
Yeah. So this theorem is at the measurable level, but then the next theorem says that anything that's measurable has to be real analytic.
And how is that proved? I mean, you said it's a correlation.
Yeah. So it's not. I mean, there. Yeah. So I could say a few words about the proofs. So this proof, for example, so this thing uses basically the curvature of Hodge bundles and random walks and a lot of analysis. And the proof that this kind of semisimplicity implies that things have to be real analytic. So the proof of that uses dynamics. So you have to look at the contracting and expanding foliations. And so you get not just real analytic, in fact you get something that's polynomial. So in fact you get that these bundles have to vary in some sense polynomial. And so, but that uses dynamics, and it uses the fact that you have this contracting foliation, expanding foliation, and you have to play some games with that. But it uses this theorem, which is proven by completely different methods. So this theorem uses just curvature estimates and random walks, and the other one uses dynamics and expansion and contraction.
And can you write down VIs explicitly, or?
No. So I can sort of try to. So the theorem that actually underlies all of this, which I have not written because. So I'm assuming I'm already in the questions period, I guess. Maybe I should say, could I just wrap it up?
Feel free to, wrap it up.
Yeah, I'll wrap it up and then I'll answer your questions about this, because I realize that this is turning into a conversation. So the point that I was trying to make is that we started with this relatively simple topological question, which is you take a torus, you wrap around the loop, and you were working on a fixed torus or a fixed flat surface, but it turns out that it's very beneficial to consider to start deforming this torus. And in fact, the dynamics, this SL2R dynamics on this stratum is in fact very strongly constrained, and it interacts a lot with algebraic geometry and with the arithmetic of these objects. And so somehow you can say a lot of very interesting things. In fact, a lot of very interesting things have been already said by McMullen, for example, and I think this is going to show up probably in the wintry course, because these L-shaped tables, they essentially come from McMullen's classification. And so these higher dimensional things also, they carry a lot of this arithmetic structure. What's lacking at the moment is good examples, because almost all the examples are via covers. But the point is that all of the structure theory kind of works, and it's very powerful, and it can already give concrete applications, like the fact that the Oseledets theorem holds for literally every flat surface rather than for almost every flat surface. So I'm going to stop there, and thanks for